they reduced it for you, now we just use it. If you want to know the induced EMF on that conducting bar, you can just do that. Or, you can do this. You should get the same motional EMF. Mark.
And the L is the length of the bar that's.
And I put L in quotes because L is this length. Why is it that length? That's the force you're trying to move the charges. They're trying to move in that conductor, that length. A lot of people still think it's this length. No. It's that length. Because that's where the charges get moving. Because that's the one that's moving transverse to the B field. So that's why I often put that in quotes. Brian first.
It's a pet question, but is it just the distance between the rails and the whole front?
It's the distance between the rails, because, well.
Because that's what changes the area that it fluctuates.
Yeah.
Oh,
Yeah.
that makes sense.
So that and that, or you can look at it, they're not part of the circuit. They wouldn't move because it's an open circuit that way.
Gotcha.
So you had it set up last week where the rails went parallel.
Yeah, the rail gun.
Yeah, how, that would then change the value of L and turn it into a differential equation.
That was, different. I can go over that again without a few things, and I'm gonna wait till I think that. Well, this, initially there's no current flowing in the loop.
Right.
You just physically move it. The rail gun, I sent current through the wire, the loop. So the short answer is, well, there's current flowing in it.
Okay.
Thus, that creates its own B field. And now those moving charges are in a B field, and they feel forces, and that's what propelled it along.
So the current wasn't induced,
Yeah, on the rail gun, I supplied the
was
current
induced?
with the battery. The magnetic field was induced around it, just because current's flowing through it. So there was no motional EMF in the rail gun.
But saying you did that, but saying, well, it just make L into an integral because now L is changing in time. So it wasn't
If you had
doing that.
If you had this situation but with non-parallel rails.
Oh, because they were not parallel, yes, that was,
Let's not do one of those.
okay.
Seconded.
So with the homework you were doing, you applied that, but yeah, it's kind of like you have two ways to look at it, They had other ones. What was it? It was, it's still BLB, it was just BLB net. That was for a wire loop and a straight wire. In other words, the second case. Now, it's the same thing, it's just the B was different on the top versus the bottom, so you had to do the net B. Basically, you had an induced EMF in the bottom rung. You have an induced EMF here. You also have an induced EMF there. They oppose each other, so it's the net effect, just like we talked about. So this is like B bottom minus B top. And generator, that's rotating the loop through the B field. This. Still, it started out as that. They just turned it into other stuff. It ended up as and explaining in a way, it's still VLB. You can see the L's in there with the area, the B's still there. The cosine is because you're changing the angle now. They're not always perpendicular, so you need that cosine. And it's dependent on how fast you're rotating it. That's the V. Pause for, some of you might be confused with that omega. Angular velocity is the omega. Remember what normal velocity is, right? Distance per time. A change in position with time, or even it's the rate at which you change your position. It's how fast you're changing your position. So angular velocity is the same thing. It's the rate or how fast you're changing your angular position. You're going in a circle now. So it is the change in your angle with time.
Does it have to be in like radians or something?
It is in radians.
So,
All right. So if you're dealing with an omega, it's an alert to change your calculator mode.
Is angular acceleration of that A with, is that, you use the?
Oh, yeah,
Yeah, alpha.
angular acceleration,
But
while I'm at it.
That's velocity.
Is alpha, that's the change in angular velocity over time, just like linear acceleration is changing in linear.
Are we doing that?
So
No,
now,
I missaid something.
so, shortcut here like you did with this, velocity is distance over time, angular velocity is your position over time. Or you can think of your position as omega t. See, this is really just cosine of theta. It's based on your the angle between them, how it's changing. The velocity v is just you're changing angular position. So it really is still just this, just because you're going in a circle. So, bottom line, if you didn't care about all that, this will probably help you. Flip It Physics derived that out for you if you want to rewatch it, or I can share it with you sometime. How they got from here to here. But again, motional EMF, you get it that way. Or you can just look at how the flux is changing. Same answer. Well, I got somebody's question unanswered. Anybody feel like that? All right, well, I guess the climax of our semester then is this.
Make it count.
That the induced EMF, that induced motional EMF, again, it's called motional EMF because it's induced this way through a change in flux. But that's the same thing as a difference in potential, electric potential, which makes the currents move. Do you remember how we found that back in the electricity units? True. When we got the circuits. The 4 circuits. We integrated around a loop and added up all the electric field around that loop. Similar to Ampere's law, you can add up all the B fields around loops we started by, and then all the E flows around the loops. Mike,
We using that V as velocity or voltage?
this is voltage. When everything was perpendicular and constant, and the V was EF. Well, that was another way back when now, of looking at electric field, it's the voltage per distance. 100 volts per meter. 1,000,000 volts per centimeter, whatever it was.
No, we were moving
Yeah.
charges away from.
We were moving charges,
Oh,
yeah. What was the electric field was defined as, anybody remember that? Way back when. Charges.
Force per charge. And the distance between them.
AQ.
You said?
Force per charge. Q over pi squared.
Force per charge. Well, that was Coulomb's law. So you plug that in, and a lot of you were saying what that reduced to. But yeah, that was the definition. And then we learned through this, that it's just another way to look at the electric field. Point is here, the induced motion EMF is that. All of that. That's the connection between electricity and magnetism. So what's this through Faraday's law? It's the change in the magnetic flux is equal to that line integral around the loop. That, I'm gonna write it out. What is the flux? Way at the top. Flux is the surface integral of B dot dA. That's the flux. The induced EMF is how it changes, and then gives us the voltage, the electric potential around that loop. This is still Faraday's law, just in all its glory. That's how I remember it, just this. Induced EMF is that. It's just reminding us that the induced EMF is that voltage. So, that's how B fields are related. Magnetism is related to electricity and vice versa. A change in one creates the other, and vice versa. And we just did a bunch of examples. We could move the loop, or we could change the current, or we could do both. If you get an induced EMF in that loop, let's say this one over here. Got an induced EMF in there. Let's say the loop has a certain resistance. And let's say this is 2 volts, and that's 10 ohms. We just talked about the induced current, why it's established, which direction it's going. How much is it? How much is the current? Not just that it's there and which direction it goes. 0.5. It's Ohm's law. E equals IR. So the induced current is the induced voltage divided by the resistance of the loop. And that is just that induced motional EMF that we find. So in this case, it's 2/10, 1/5 of an amp, is how much current is actually